So with Mohamed we will talk about leveraging machine learning techniques for automating ticket routing. Let me start with agenda. I will introduce the problem, how our company is split into multiple organizations, where we found area that can be improved, let's say, how important it is to set proper metrics, and how we can measure performance of a tool which already altered the system which is defined. Then Mohamed will tell you a little bit more about technical stuff, about one of the solutions. Then we will have a little bit time on conclusions, I think. So let's start about the organizations. Our company's product is very big and complicated. So it's not surprised that we have multiple organizations. Each of them is responsible for a different part of a product. Here we can see the general ratio of them in perspective of involvement in tickets. I named only the first three in sake of the presentation, and also choose name alpha, beta, and gamma, also to be more clear and don't use complicated names, let's say. In this presentation, I will focus on the alpha organization. Okay, so I said before that the ratio was in regards to involvement in tickets. So what is the ticket and how the very general view of the life cycle looks like. When something works not as intended, or when some test fails, the tester opens a ticket. It's a request for improvement to correct some bugs and wherever. But the tester here only see the symptoms and have some hypothesis. The product is too big to know a root cause of those symptoms. And he needs to choose a group which will correct the problem. But before that, the investigation is needed to actually find the root cause. And this is a reason why most of our organizations has entry group, sometimes even more than one. The job of the entry group is to correctly identify the problem and ideally find the root cause and to assign proper development group to introduce the corrections. After the corrections, the ticket is of course closed and everything is good. Let me tell you a little bit more about the entry groups here, because it's a good part of my part of the presentation. They are very important in our company because, you know, if the product is so big and we have so many development teams, it's not possible that the tester will pick the correct one. So the job of a tester is to only assign to correct organization, and the entry group is, let's say, responsible for the, you know, handling the ticket at first. So to investigate what is the problem, to identify the correct development team. This is a very hard job because all of those teams have to have very wide knowledge about the whole product. And yes, a little bit more about the development teams, but just a few words. They are very specialized in their field, so they don't know enough to whole product, and they are focused just on little part. and they are responsible for the correction, as I said before. One more thing here, the ticket can be handled by multiple organizations, not just by one. Sometimes multiple corrections are needed. Okay, so to summarize this part, the few key sentences. The tester usually see only the symptoms. The root cause is very hard to detect. The product is very complex, and the job of the entry groups is also very hard because they have to have very wide knowledge about the whole product. And each transfer needs a reason. It's something obvious to have a reason why someone thinks that another group need to be assigned to investigate, but this is something that needs to be said because it's very time-consuming and so it's costly. You are probably guessing where we can find the areas of improvements. But we will focus here only on the first part of choosing the entry group by the testers. Here we can see very similar plot as on the very few first slides. Here the organizations are the plot is combined from the tickets by the assignments. So when the tester assigned a ticket to entry group, then we can see here which organization is assigned the most, and it's not surprised that the first biggest three organizations are also here. But there's some kind different view is in this slide when we compose this plot only from the tickets that were incorrectly assigned. What I mean by that is when the organization, when the entry group of the organizations get the ticket and they are assigned by the tester, but the organizations wasn't responsible for the problem. They didn't introduce any of the corrections. And we can see here that the alpha organization is the first one, with the biggest one with this problem. Mostly because the alpha organization is also responsible for the part of the product that in which most of symptoms are visible. So it's also not something difficult to guess that such organization will be chosen incorrectly, not most of the time, but often. Okay, what can we do about this? Fortunately, we have something like the decision support system in Nokia. It's something that can be used to help tester identify the correct first entry group. The decision support system have multiple subsystems underneath, but here I will talk only about those two. The first one is for the verification process, so it can be used to check if the description, maybe title of the ticket is composed correctly, if it follows fault management standards. But the second one is in this presentation, the second part, the suggestion system is more interesting here. What I mean by that is this subsystem can predict which entry group can be used as first assignment. Also, it suggests which tickets were described similarly that in the description that tester provide. So here we also thought that we can add another subsystem here. So very simple one, only for saying that, hey, this ticket doesn't sound like it should be handled by the alpha organization. So maybe consider something else, someone else, some organization else. And we did that. I would like to say a little bit more about the metrics here, because when we create this model, it turns out that our initial goal to have very high precision wasn't enough. But let me tell a little bit more about this slide. It's composed from the dummy data only just for sake of this presentation, but the general shape I think is preserved. I think our target was to have very high precision in detection to detect not alpha organization. And we achieved that. The precision was very high. We are even surprised how high it is. It's not visible here because it's an exaggerated graph. But we have very high precision. However, it's not something that we should focus about, because when we split the cases of the predictions into two tables and thought about each case separately, then we can see that not all rows are important here. In the first table, we can see that our model not always says something. It sometimes is silent, because when the model predicts is alpha-related pronto or ticket, or it's not alpha-related ticket but with not high enough confidence, then it becomes silent and doesn't say anything. Here, the second row is most important, because it's actually our problem we would like to solve when the first assignment is alpha, but alpha wasn't involved in corrections of those tickets. So yeah, this is the problem we would like to solve. But as I said before, the precision was our initial goal, because only with high precision we can use such tools in decision support systems, because if one sees that something tells sometimes wrong predictions, then such tool won't be listened anymore. So high precision was very important for us. However, when we look about this from the business perspective, only those two first rows was important, I mean, in the second table. So when the first assignment was alpha, but the model thought it's not alpha, and we have two cases here. Tester was right, and those cases are very negative, because we actually adding more work to the system. We introduce even more noise. But the second row, when the model was correct, is a very positive one, because our goal is satisfied here. We reduce the incorrectly assigned alpha organization tickets. What is surprising here, the last two rows aren't important from the business perspective. Even when the model is incorrect and say, hey, this ticket isn't alpha related, but author has the same opinion, then nothing in the system is changed. This isn't good prediction, but none that can impact the system. However, we still have to monitor the precision, because as I said before, gaining trust and holding it from the user perspective is very important in the decision support systems. Okay, our tool has good metrics, even if we talk about the business impact. So we introduced this tool, but we create another problem here, because how we can measure performance of such tool if we alter the whole system, because sometimes a tester needs to or listen our prediction and we lost the initial guess, let's say. The solution is simple. We use A/B testing. It's something that can be described as we have multiple predictors and we randomly choose just one to show the prediction to the end user. The ratio which predictor is chosen is customizable, so it's also fine here. We almost most of the time choose our system, but the other predictor is a dummy one. It always says nothing. Like even if the real predictor says it's not alpha-related ticket, we sometimes need to say nothing, just to have a couple of samples to measure the performance of the tool. Okay, so from my side, the most important lesson we learned are that custom metrics sometimes are necessary, and the precision recall are good, but they are not enough to justify a reason why we should introduce the model in the system. Something more thoughts are needed here. And A/B tests are good method to measure performance of a tool which affect the system. Okay, this is all what I have for my side, but Mohamed will tell you more about one of the solution with more technical details. So Mohamed, please go ahead.
Thank you, Gabriel. Can you hear me, everyone?
Yes.
Okay. All right, so let's move to the second part, which is related to the deep contextualized language models for automatic ticket routing. So this is the outline of my part. So I will start by a background section about the embedding techniques in general, so from the traditional to deep contextualized embeddings. And then I will present the attribute level model for development unit prediction, and I will finish by the conclusions. So now let's move to the background section, and let's start by the traditional word embedding. So here suppose that we are given this sentence and you would like to build an embedding for each token here in this sentence. So suppose that our target word is the token apple. So in the literature there are actually two famous models, which are the continuous bag of words and the skipogram model. So for the continuous bag of words, it uses the contextual information. So this contextual information is defined as a window of tokens around the target word. So here the window size is equal 3. So we have 3 word token to the left, 3 token to the right. So these tokens are used as input to the embedding layer in order to obtain the context vector, which is forwarded to the classification layer in order to predict the target word. So the skipogram is actually similar to the continuous bag of words, except that it's in the inverse direction. So here from the target word, we try to predict the context tokens. And here in the literature, it has been shown that the skipogram model works better than the continuous bag of words. But here in both cases, we obtain context and dependent embedding for every token, regardless of the syntax and the semantics, which means that here this embedding does not handle the polysemy. Polysemy means that a given token can actually have different meanings. And that's why in the literature, the contextualized embeddings is proposed. So here we want to represent not just the meaning of a word, but also the word in the context. So here I'm showing an example of polysemy for the token apple. So it's used as a product in the first sentence and as a fruit in the second sentence. And usually to capture the contextualized embedding, the RNN or the current neural networks are used. Here I'm showing just an example of RNN with two layers, and the output of the second layer is considered as the context-aware embedding. But here, although we obtain context-aware embedding, these embeddings are not deep in the sense that the embeddings are not a function of all the internal layers of the RNN. So for example, for this token apple, the embedding is only a function of the last hidden state, but this first hidden state does not have a direct impact on the embedding. And you would like to have deep embedding because you want to capture rich word representations. So what we can say here, we have a context-sensitive embedding for each token obtained from the last layer of the RNN, but this embedding is not deep. Let's move now to the deep embedding, and we will use BERT as an example. So BERT is the bidirectional encoder representations from the transformers. So the representation from BERT is deep because it's based on the transformer architecture. So in the transformer, a token representation is a function of all the other tokens and also a function of all the internal states. And also the representation from BERT is bidirectional because it fuses the left and the right context. And usually in BERT, so we have two phases, the pre-training phase and the fine-tuning phase. So first of all, BERT is pre-trained on large corpus of text data for two unsupervised tasks, which are the mask language modeling and the next sentence prediction. And then this pre-trained BERT is used on downstream task. For example, here we are showing the spam detection as the downstream task. So to handle this pre-training and fine-tuning, BERT introduces several special tokens. So the first special token is the mask. So suppose that you are given this original sequence. So here BERT randomly masks percentage of tokens from this original sequence using this mask token. And then BERT tries to predict these masked tokens. And this is known as the masked language modeling. For the fine-tuning steps, there are actually two settings, the single sentence and the pair of sentences. So the single sentence is related to cases where we have a single input, for example, the document classification. And pair of sentences, we have two inputs, for example, the document retrieval, we have the document and the query, or the question answering, we have the question and the answer. So here BERT introduces the second special token, which is the CLS. So here the CLS is added to the beginning of this sentence so that the embedding of the CLS is considered as the embedding of the whole sequence. For the pair of sentences, so BERT introduces the third special token, which is the SEP. So here the SEP is used to concatenate both sequences, and then it's treated as a single sequence so that the CLS token is added to the beginning. And similar here, the embedding of the CLS is considered as the embedding of the pair of sequences. So we can say that here we have deep bidirectional embeddings that is obtained from the transformers and used for the downstream tasks. So now let's get more details about the BERT architecture, and let's open this yellow box. So actually BERT is composed of multiple encoder layers. And the first important parameter is the number of layers. So this parameter decides about the size of BERT. For example, BERT base has 12 layers, BERT large has 24 layers, and the small scale of BERT has 6 layers. Now let's open this encoder box. So it's composed of the self-attention and the feed-forward neural network. So we are all familiar with this feed-forward neural network, but what is this self-attention layer? So let's open this box. It's composed of multiple layers of attention heads. So here the second important parameter is the number of attention heads. For example, there are 12 attention heads in BERT base and 24 attention heads per layer in the BERT large. So here BERT is composed of multiple layers and each layer has multiple attention heads. So now let's have more details about these attention heads, and let's show the computation of one embedding within one attention head. So suppose here we are given an input sequence. So this input sequence is actually composed of two tokens, thinking machine. So here we have the embedding of this of each token, and then there are three parametric matrices that are introduced, which are the query, the key, and the value. So we multiply the embedding of each token by these three matrices in order to obtain the queries vectors, the keys vectors, and the values vectors. Now, these vectors are actually used to compute the self-attention embedding. So for example, for this first token thinking, the attention score is computed by multiplying the query vector by the keys vector of all the tokens. For example, here the first score is computed by multiplying Q1 with K1, and the second attention score is by multiplying Q1 with K2. And after computing this attention score, these scores are normalized by dividing with the square root of the embedding. And then the softmax is applied so that the sum of the attention scores are equal to 1. And then the softmax attention scores are multiplied by the value vectors in order to obtain the weighted values. And then these weighted values vectors are summed in order to obtain the final self-attention embedding. So the same steps are applied to each of the tokens, of course, with the corresponding attention scores. So here we can say that query, key, and value vectors are computed to obtain a self-attention embedding for each token. Now, how can we compute the self-attention embeddings for all the tokens? Because here we will not repeat this operation for each token. So in the real implementation, matrix multiplication is used for this purpose. So suppose we have the input embeddings for all the tokens. So they are multiplied by the query key and value matrices in order to obtain the query key and value embeddings. And then with an efficient matrix multiplication, we obtain the final self-attention embedding. So here, these attention scores are simply the softmax of the query multiplied by transpose of the key and then normalized, and then applying the softmax. So this matrix is actually the attention matrix for all the tokens. So it's, for example, if we have n tokens, it's an n by n matrix, and then multiplied by the value vectors in order to find the final self-attention embeddings. So here we can say that matrices multiplication is used to obtain a self-attention embedding for each token. Now, for the multiple heads computation, so each layer, it has multiple attention heads, as I explained earlier. So we have the embedding as input, and now instead of having a single attention head, which is composed of query key value matrices, so here we have multiple attention heads. So here we are showing 8 attention heads, and from each attention head we obtain the self-attention embeddings. So this Z0 until Z7, and then these embeddings are concatenated and multiplied by another multi-layer perceptron layer in order to recover the initial embedding. So here the dimension of the final embedding should be the same as the dimension of the input embedding. So here we can say that multiple heads are introduced to obtain multiple representations. So here I wanted to show example of real attention score or attention head matrices. So this is actually the softmax of the key the query multiplied by the key transpose and normalized. So here I'm showing some attention heads from a project that I worked on. It's related to the semantic labeling. So here I'm showing, for example, first attention head at layer 3 and 11th attention head at layer 12. So here I'm showing the same attention heads, but for 2 different examples. So here the X and the Y are actually the tokens, because here we are computing the self-attention of a given token with respect to all the other tokens. Yeah, and as you can notice here, we have more tokens in the first example than this second example. And you can notice that we have different shape of attention matrices and different contribution for every token. So here the darker the color is, the more the higher is the attention score. This last one is actually very special one, because here this attention head focuses only on this token. So we say that this token from attend to all the other tokens, or we can say all the other tokens are attended by this token. So here, as a conclusion, we can say that attention heads can have different distribution of weights. Okay, this was a quick background about the embedding techniques with a focus on the deep contextualized language models, especially for BERT. So now let's move to the second part, which is the attribute level model for development unit prediction. So here, as explained by Gabriel, so the problem is the automatic ticket routing to the correct development unit. So whenever there is a service problem, there is a ticket that is open to describe the service problem, and usually there is a tester who decides the correct development unit of this ticket. So we would like to automate this process and forward the ticket directly to the correct development unit. But there are here multiple challenges related to this task. So first of all, a ticket is associated with two sources of information. So the first source of information is the attribute level information, which is structured information, and we also each ticket is associated with or is attached with multiple log files. So in this project, we only focus on the first source of information, and we are investigating in the future work how to take advantage of the log files. So the first question or the first challenge is how to represent each ticket using all the attributes. And the second challenge is how to take advantage of the state-of-the-art BERT model, because here the data that is used to pre-train BERT is textual data, is unstructured data, and it's completely different than the ticket data. And this second point is actually related to our future investigation of using BERT also with the log files from each ticket. So we can say here that automatic ticket routing presents many challenges. So for our proposed method, suppose that we have a huge collection of ticket data. So here, this is the pipeline of our training model. It's a multi-steps pipeline composed of 5 steps, namely building new vocabulary, building new tokenizer, representation module, pre-training module, and finally the fine-tuning module. And as output, you obtain our train ticket model. And for the testing, we have an unseen testing ticket. And using this train ticket model, we would like to predict the correct development unit. So here we can say that a multi-steps pipeline is proposed to train the model using the ticket data. Let's move now to the first step, which is related to the ticket vocabulary. So as I mentioned before, the ticket data is completely different than the textual data that is used to pre-train BERT. So here I'm showing the frequency of tokens in the ticket data. I'm showing only the frequency of the top 1000 tokens. So as you can see, the frequency actually drops very quickly. So suppose that there is a number of unique tokens in tickets, and we denote this number by X. So usually X is very large. So here I'm showing some synthetic tokens. So suppose that these two tokens are frequent in the ticket data. So when BERT faces these tokens, because these tokens are frequent in the ticket data, but they are not present in the BERT data or BERT vocabulary. And that's why here, when BERT faces these tokens, it decomposes these tokens into several sub-tokens. And actually, we don't want this to happen. So we would like BERT to keep all these tokens as a single token in the tokenization phase. Here, the solution is to add the most frequent tokens in the ticket data to the BERT vocabulary. But here, suppose that of course, from the ticket vocabulary, there are some tokens that are already in the BERT vocabulary, and we denote these tokens by Y. So usually Y is very small compared to X. And by the way, the size of BERT vocabulary is equal to 30,522, which means that we need to select some tokens to be added to the BERT vocabulary, and we select these tokens based on the minimum frequency. So for example, the minimum frequency within the top 1000 is X1, within the top 3000 is X2, 30,000 is X3. Of course, X1 is larger than X2, larger than X3. And based on this empirical analysis, so here we choose some tokens. Unfortunately, I cannot say the exact number of tokens that we added, but we choose some tokens from the ticket data that are added to the BERT vocabulary. So we can say that a new vocabulary is built for the ticket data. So for the ticket tokenizer, so here we prepare a new ticket tokenizer using the ticket vocabulary. There are 3 important files that should be prepared, which are vocabulary.txt, tokenizer.json, and add.tokens.json. So here we save the new ticket tokenizer in the vocab.txt, and we save also the new ticket vocabulary using the dictionary. And finally, we have special tokens that we added, but here also, unfortunately, I cannot give more details about these special tokens that we created. And here we can say that the new ticket tokenizer files are used to initialize the tokenizer in pre-training and fine-tuning. Let's move now to the representation module. So we have multiple attributes that are available for each ticket. Suppose that we have M attributes. So for the challenges here, we would like to use all the available attributes, and we would like to aggregate the information from multiple attributes. Also, the attributes should not be treated uniformly, because there are some attributes that are more important than others for each ticket, and the important attributes will be discovered during the fine-tuning phase. Again, here we cannot show our proposed representation, which denoted by rep ticket, because this representation module is part of materials that are submitted for a patent for reviewing. So here we can say that we obtain a specific representation of the ticket from the representation module. For the pre-training module, so here before aggregating the attribute level information for the tickets, it is very important to understand the relation between the attributes. So here we would like to find the hidden correlation between ticket attributes that is impossible to discover by a human. And again here, we cannot show this proposed pre-training task because it's also submitted for a patent. But what we can say here is that we want to discover hidden correlation between the attributes. For the fine-tuning module, so for the motivation, we would like to aggregate the correlation of ticket attributes in order to predict the development unit. Here we use the same representation also for the fine-tuning stage. And in this aggregation phase, it is important to, the importance of attributes is captured using the self-attention scores that are computed in the attention heads of the transformers in BERT. So if you recall, so we have this attention matrices that are computed using the matrix multiplication between the query and the transpose of the key. And actually, these attention matrices are very important in order to capture the contribution of each attribute. So here we can say that the attributes are not treated uniformly thanks to these attention heads from the transformers. So here the fine-tuning module should capture both the attribute position and importance. For the model overview, so here we want to aggregate the attribute level information of tickets to predict the development unit. And here we use the available labels of tickets from the brain split for the attribute level aggregation. So I want to show this. This is similar to using, for example, BERT for spam detection or any downstream tasks. So here we add the special tokens of BERT with the representation of the ticket. And here the fine-tuning model is composed of the pre-trained model and the multi-layer perceptron. So here we obtain deep contextualized embeddings from the pre-trained model for each token. And here we pull the embedding from the CLS token. So this is similar to the spam detection, for example. And finally, we forward the CLS embedding to the multi-layer perceptron to predict the ticket's label. So here we can say that the attribute level aggregation or the fine-tuning module is composed of the pre-trained model and a multi-layer perceptron. So for the evaluation metrics, we have, first of all, we have these splits for data training, validation, testing. Obviously, here this data is not balanced. We have significantly larger tickets that belong to the non-alpha compared to the tickets that belong to alpha. So as the first evaluation metrics, we report the F1 score of the alpha class, but also as explained by Gabriel, we would like to prioritize the precision over recall for the alpha class. That's why here we need to choose a lower bound of the recall on the validation set. And then we select the threshold on the predictions of the validation set that maximizes the precision while keeping the recall larger than the lower bound. And then we select the best epoch on the validation set with the maximum precision. Of course, we need to make sure that the recall is larger than the lower bound. And finally, we output both the best epoch on the validation set and also the threshold of the confidence scores. So F1 and precision of alpha class are used as main evaluation metrics. So for the results, our proposed method achieves high classification results in terms of precision and F1. So we have an increase of F1 score by 4% compared to the human performance. In terms of ablation study of our full model, which is composed of the new vocabulary, pre-training, and the fine-tuning, we have an increase of F1 score by almost 8% compared to the fine-tuning without the pre-training. We have an increase of F1 score by 2% compared to using the original BERT vocabulary instead of using our new vocabulary. And when we prioritize the precision, we have a decrease in the F1. Of course, we will have a decrease in the F1 score here by almost 10% compared to the prioritizing the F1 score. And we have a significant increase in the precision by almost 19% compared to prioritizing the F1 score. So overall, we can say that our full model achieves high classification results in terms of F1 score and the precision. And to conclude here, we proposed an attribute-based model for ticket classification. Our model is composed of multiple steps, which are building new vocabulary, building new tokenizer, representation module, pre-training module, and fine-tuning module. And we show that our model achieves high classification results in terms of precision and F1 score. And for the future work, we would like to solve the multi-label classification of tickets, so by considering multiple development units. And also, we would like to generate a summary for groups of similar tickets that highlights the important characteristics of a given group of tickets. And that's all for my part, and thank you.
Okay, thank you, Mohamed and Gabriel, for a very interesting presentation. I don't see any questions in the Discord platform, so let's open up the floor to our audience here in the Multikino. Do we have any questions for either Gabriel or Mohamed? Okay, if no, let's warmly thank them once again for a very interesting presentation. Thank you, Gabriel. Thank you, Mohamed.
Thank you, everyone.